Hello, my name is Nikolic, and here I present BitPruning. This is our novel method for learning the optimum number of bits required for inference of neural networks.
The main question we are trying to answer is how much information we need in each part of the network. We've seen that 32-bit floating point is definitely enough. However, many applications can be solved with 16 and 8-bit fixed point, and some with even less. There is no good way of figuring these out up front. We basically have to guess prior to training. We propose that the number of bits can be learned during training. To do this, we treat bitlengths just as we treat all our parameters, and use gradient descent to update them during training. We first have to redefine the meaning of bitlengths to make them differentiable, and then penalize them in the loss function. To rephrase the problem, smaller bitlengths have a profound effect on energy efficiency and performance. When we represent the required information with less bits, we can discard any unused ones. Memory storage and data transfer get smaller, leading to reduced energy consumption and chip area. We can also reduce the compute workload by using dedicated hardware with bit serial or spatially composable designs. All of this saves the environment by reducing energy costs. However, it can also help push deep learning towards the edge, reducing the need to communicate with centralized data centers and thus improving privacy. We achieve all of this with BitPruning. Okay, so let's do a quick review of how neural networks learn. On the right, we have a diagram of a neural network. Each circle represents a neuron whose output value is calculated as a weighted sum of its inputs and a differentiable nonlinear function. The weights of the weighted sum are parameters whose values we try to learn. There are two stages in the training process. In the forward pass, we propagate the input through the network and onto the output where we calculate a differentiable loss function. This function is just a proxy of how good or bad our guess is. The more off the guess is, the greater the loss should be. Once we know how good the guess is, we want to improve it. This is done iteratively in the backward pass. We need to find how to modify each weight to reduce the loss. This is done by calculating the partial derivative of the loss with respect to each weight and then updating in the opposite direction. This can be done by propagating gradients backward. This is why we need each operation in the network to be differentiable. This is a basic description of a gradient descent, and we want to use the same method when learning bitlengths along with the weights. However, we have two problems. The first is that in the fixed point domain, the derivatives when quantizing weights and activations end up being zero everywhere except when we have jumps in value, where they are not defined. Thus, the backpropagation of the gradient is impossible. An even bigger problem is that the bitlengths are undefined everywhere outside the integers, and the quantization derivative in respect to bitlengths is non-existent. So, how do we solve these problems? First, we define a learnable bitlength. From the description of the gradient descent, we need to make the quantization differentiable. Let's first solve the vanishing gradient of the weights and activations by defining quantization for integer bitlengths. This problem has already been previously solved by a straight-through estimator. We simply define the quantization for integer bitlength to be a uniform quantization between the largest and the smallest element in the batch. The straight-through estimator, which quantizes the values in the forward pass and treats them in their full 32-bit floating point format in the backward pass, allows for the gradient to be properly passed. In essence, it declares the derivative to be 1 for the quantization step. In the second problem, the derivative in respect to bitlengths requires the definition of a continuous bitlength. We do this by simple interpolation between the nearest two integer bitlengths. For instance, a value represented by 3.3 bits is equal to the weighted average of the values represented by 3 bits and 4 bits, where the weights are the distance between the non-integer bitlength and 4 and 3. This provides a simple yet reasonable way of propagating the gradient back into the non-integer bitlength. The next step is to make sure to penalize bitlength in the loss function. We do this by adding a simple L1 loss of the bitlengths with the modification which allows the bitlengths to be prioritized and weighted. This means our bitlengths will reduce together with the error. In this formula, we use lambda to prioritize different groups of bitlengths alpha, and we use gamma to choose the strength of the regularizer. This approach can be applied at any granularity. Finally, we can apply the gradient descent algorithm as usual. However, this process will lead to non-integer bitlengths. Since no hardware can run these, we need to round them up to integers and do some fine-tuning. Okay, let's take a look at some results on Cypher 10. We trained AlexNet and ResNet 18 with 32-bit floating point baseline and per layer bit pruning versions with different regularizers, but all with equal weighing of the bitlengths. All versions, including the baseline, have been trained for 300 epochs with 1 cycle policy. The bit pruning versions have been fine-tuned for another 60 epochs with their bitlengths rounded up. Let's first look at the AlexNet graph on the left. On x-axis,
we have epochs during training, while on the y-axis, we show top 1 validation accuracy in solid line on the left, and the number of bits in the dashed line on the right. The CN line shows the FP32 baseline, while the rest represent progressively more aggressive quantizations. The number in the legend represents the gamma parameter. The graph shows that the Bitlengths drop quickly and level off by epoch 30, and then remain mostly flat for the rest of training. We can see that when the number of bits drops to the near final values, we have a noticeable accuracy drop. The more aggressive the quantization, the bigger the drop. However, most of the drop is recovered by the end of training in all cases. The only exception is the most aggressive quantization of AlexNet, which crashes. At epoch 300, we round up all Bitlengths and continue training for another 60 epochs. At this point, we see a noticeable accuracy drop. By the end of fine-tuning, we recover almost all of the lost accuracy. ResNet 18 shows a similar story on the right. We can see the same trend for Bitlengths, but all BitPruning versions track the baseline accuracy. ResNet is presumably better at absorbing the losses created by quantization. Similarly, the drop of accuracy when the Bitlengths are rounded is not noticeable in ResNet 18. Finally, you can also note that the aggressive version of ResNet, the brown one, hasn't failed. It bounced off and found a solution which produced a better accuracy with a larger bit length. While the stronger regularizers will generally produce smaller bit lengths and greater accuracy drops, this isn't always the case. We can also use BitPruning to target any quantifiable criteria. This is simply done by modifying the L1 loss to be weighted by simply changing lambdas in the formula. In this case, we demonstrate how to reduce according to memory footprint and operation count. In the table, we have results for 4 versions of AlexNet and ResNet respectively. Column name target indicates a modified function to target a particular property. Regular represents the unweighted one. Batch sizes 1 and 128 represent a weight and activation heavy network, while MAC represents total number of multiply cumulates per value. The accuracy column shows validation accuracy. Here we see that the accuracy may vary, however the regular one appears to be worst in all cases. In the non-integer rows, we show weighted average bit length, depending on the target property. We do the same with the rounded integer Bitlengths. Since only the numbers in the diagonal are matched, target and criteria, we expect these to be smallest in each column if our approach works. We see that this is the case and that the modifications are very efficient at targeting each property. Okay, let's switch gears to something more serious, ImageNet. We trained the bit pruning networks with regularizer parameters such that an 8-bit network would produce an additional loss of 1 with equal weighing of Bitlengths for 180 epochs in one cycle policy, while the baseline is trained for 90 epochs. This is because 90 epochs bit pruning was unable to match the baseline accuracy. Since we are targeting inference performance, we doubled the number of epochs to allow for best possible results. The loss of time and energy in training will pay abundantly in saving of time and energy during neural network use. Here are the accuracies after training and fine-tuning. The blue bar represents the 32-bit baseline. The red one is the accuracy of the learned non-integer network. We see that it is roughly the same, a bit smaller for AlexNet, a bit better for ResNet and MobileNet. Now the yellow bar represents the final integer bit length accuracy after fine-tuning. These are accuracies we will get once the network is deployed. They show only a slight dip in accuracy versus the non-integer version, and roughly the same as the baseline. It is also important to look at granularity. The learned per layer bit lengths for AlexNet, ResNet, and MobileNet are shown here. Although the average in all networks is around 4 bits, we can see that they vary wildly. The graphs show layer bit lengths in a breadth-first manner. Activations are red and weights are blue. Furthermore, we see that first and last layer generally require more bits. Weights always appear to be better than activations. This is an important consideration since if we take a whole network approach, we would have to use the worst case scenario, the largest per layer bit length we see here. Lastly, I will talk about performance and footprint results from simulations. The reference point used is the 8-bit baseline, since we know it usually works. On the performance graph, you can see the improvement we achieved on the 4 different hardware accelerators. Stripes and DeepRed are both bit serial designs on the activation side with different granularities. Loom does the same approach on both sides of the calculation. BitFusion is a bit parallel spatially composable design. As you can see, bit pruning does significantly better on all. The least improvement we got is on Stripes and BitFusion, a bit less than twice. On more aggressive ones, like DeepRed and Loom, the improvement is around 4 times. The memory reduction potential graph might be even more important. In addition to the design shown on the left graph, all with on-chip compression, I plotted the off-chip compression of Proteus, a design that smartly packs values to minimize footprint. We got small reduction for stripes and deep red, but much bigger 50% reduction in off-chip memory footprint for Proteus. The biggest reduction, 75%, we obtained for Loom, the most aggressive on-chip compression. I covered only a few of the results of our project. In the paper, you can find a lot more. To conclude, we introduced our BitPruning method to learn the number of required bits for accurate inference. Our approach works for arbitrary granularity, and we can prioritize any criteria. We showed up to 4 times performance improvement, as well as up to 75% memory footprint reduction on proposed accelerators on ImageNet. Thank you for listening. If you have any questions, send me a message and I will be happy to answer. Take care and stay safe.